Okay, welcome everyone, and thanks for joining my talk. So today I'm going to talk about eBPF and try and give a small introduction to it. During the talk, I'm probably going to switch between calling it eBPF and BPF, but I will always mean the extended BPF, not the classical one, if you're familiar with the differences. So I'm Martin. I work in Cisco, been there for many years now. Basically all I do is very Linux-based these days. And so I like digging into fun Linux APIs, like BPF. But in this case, I really have no idea what I'm doing. I decided to submit a talk on something I wanted to learn something about. So I learned a lot. I'm not really sure how much the abstract meets the actual content anymore, because I started writing and stuff changed. Hopefully it's not too far off. But yeah, I wanted to experiment with eBPF, and the way to allocate some time for that is to submit a talk, obviously. Which might, in hindsight, have been a mistake, though it was fun. But don't use any of the code in this presentation. First off, it's presentation code. There's a lot of error checking and stuff missing. It will blow up, and there's probably way better ways of doing some of the stuff I'm doing. But hopefully it'll give you an insight into how you can start using at least parts of, or some of the systems that use eBPF to do cool stuff. So what is eBPF? And the short of it is there's a way to program the kernel, or program the kernel without modifying the kernel source code or any kernel module source code. eBPF in itself is also a programming language, and the programs that you make with it, they're event-driven. So basically what you do from the user space is that you create a binary program which you send into the kernel, and you hook that program to some kernel-defined hook. And then when that hook hits in the kernel, for instance, you're opening a file, then your program will evaluate. So in the kernel, there's an interpreter for this programming language. There's also a JIT compiler, which is pretty cool. And the big gain of this is that you can add features to the kernel, meaning they will run without having to cross the kernel user space barrier. So you can modify the kernel without having to patch the kernel, then compile the kernel, or even worse, if you want to make this available for everyone, you would have to patch the kernel, try and upstream that kernel patch, go probably quite a few rounds, eventually get it upstream into the kernel, and then you have to wait for every distro to pick that new kernel version up, which is a long way. So with this, you can just, hey, I have this eBPF program, send it out to people and they can run it. Now, running binaries inside of the kernel that comes in from user space sounds like a very scary thing, and it kind of is, because the kernel is something you want to protect. If the kernel goes down, everything goes down. So can I harm the kernel or get information from the kernel that you shouldn't have access to? Well, first off, the loading of eBPF programs they need correct capabilities, which in this case is cap BPF. In most cases and on most systems, you need this capability. There are some exceptions if you compile the kernel in a way that allows it to run unprivileged BPF programs in some subsystems. But generally, cap BPF is necessary. But when you load, if you have the correct capabilities and you load a program, an eBPF program, into the kernel, there's some checks happening. So there's a verifier which checks that, it tries to check at least that it doesn't crash or harm the system. And some of the limitations on this is actually in the programming language itself and its limitations. It checks that you're not using an initialized memory. It checks that you're within a size limit of the program size. And it checks that your program has a finite complexity, meaning that at some point you can prove that this program will finish. So you can't have infinite loops. You need actual bounds on your loops for this to even work. It's also running in a protected execution context, so you only have access to the memory that is sent into your hook, or you have to use some helper functions to gain access to memory outside of your protected memory region. So that would then go into the kernel memory and do a lot of checking before copying that data structure into something you have access to. And there's the memory for the program itself is as soon as it's past the verifier, it's set to read only. So you can't modify a running eBPF or a loaded eBPF program anymore. So there's a lot of, it's gone some thought into this. They are trying to save your system, even though you write shitty eBPF programs. Hopefully you won't be able to harm the kernel. But why is this a cool feature or a set of really cool features? Like I said, you're now able to do actual kernel features, meaning in this case, avoiding sending stuff up and down the user space kernel barrier, which is expensive. And you can do it for stuff like monitoring and tracing processes. You can make decisions based on what's happening on the system in these cases as well. You can do the same for networking. So this can be used to, for instance, collect data on how a system is used, or it can be as a protective layer to make sure that only certain processes can do certain things, or they can make decisions on the networking layer. For instance, you can proxy everything through something else without the user space even knowing, because every decision like this happens in the kernel space. And also all the cool kids in the kernel space these days uses eBPF, so that's a good reason. After I submitted this talk, we got an actual use case at work for doing this even. So what we wanted to do was, when a specific process is exec, so basically when you create a specific process, we want to put that into a memory Cgroup to limit the available memory for it, to have it not kill all our servers. And that's the use case I'll be using in the presentation. So we'll kind of go step by step through how to do something like that. This is my overview of eBPF and how it's loaded into kernel and what happens. So we start in the user space, where the green program here is actually the one loading the eBPF program into the kernel using the BPF syscall. Where's my pointer? Yeah, it's gone. Then that runs through the verifier. If it's verified, it goes through the JIT compiler. And then we have an eBPF program that's loaded into the kernel. And it's also created some maps. Now these maps are the communications between user space and kernel space, or between user space and your eBPF program specifically. Now this eBPF program is hooked into one or several of the hooks on the right here, and you can have hooks on like system calls that's being executed. So for every time someone opens a file, you can monitor that. The same with devices that are being accessed, or well, like I said, networking. And you can also put an eBPF program on a Cgroup itself to, for instance, manage traffic, network traffic for that specific Cgroup. Then there's a lot of these hooks in the kernel. And then when a program basically hits one of these hooks, it goes into kernel space, it opens up a file or a device or sends a packet on the network, then your eBPF program, which is not part of the calling program, is doing its evaluation. There's quite a few tools that you should look into when you want to make an eBPF program. So libePF is the C library that I'm using to basically make life a lot easier when creating eBPF program. It does a lot of lookups for finding maps, and it does a lot of stuff for me. BPF tool is a tool for both inspecting and manipulating eBPF programs, and it'll also help out by making a skeleton, for instance, which is very easy to use from your userspace program to get access to the maps and to create and load the programs. BCC I haven't used, but it's a toolkit for creating eBPF programs, for instance with Python or Lua. So you have to write the C code, and then BCC will facilitate compiling the C code to BPF and send it over to the kernel. And Clang is very nice. It has a BPF backend, so you can write C code and get out a BPF program instead of using a lot of kernel macros to create a binary that is where the code you write is almost completely unreadable, and doing a bit more advanced stuff is definitely not advisable. Netlink is a kernel API that allows you to, in this case, it's a socket type that allows you to attach a BPF program to a kernel interface or a specific part in the networking stack. It's not recommended to do this directly, but use the IP tool instead, which uses Netlink to do the same things. Because what you'll figure out when you start looking into eBPF is that there are many hooks, and a lot of these hooks have different ways of attaching a program. So doing eBPF for system calls versus for networking, the way to attach to whatever you need to attach to is different. So let's start with a small example of a BPF program. And this is a full BPF program. Now, this sec macro defines a section in the BPF program to use. Basically, this defines the hook. So I'm hooking into the trace point sched process exec. So every time something runs the exec syscall, this will run. Now the memory context I get for this trace point is the trace event raw sched process exec, which has some members, and you can use. You have to kind of look into what the members actually are, but this is basically your execution content. This is what you have access, the memory you have accessible from kernel space. The name, you can choose to name it whatever you want, because this is just C. Then we have this BPF core read, which is a helper function to help reading out the memory from a structure. And this BPF get current task is basically one of the helper functions to get information about the current task into BPF space. That's not something you have access to normally, unless you use this helper function to get that memory region. So basically what I do here is I check I find my PID, I find my parent PID. This reads a string from the kernel, which is in this case my the first argument of the exec system call, which is the file name that you're trying to exec. And then I do just print out that information. Now at the end here, I also have a license, which I put in the license section. And that's required. It is required to have a GPL compatible license that you're using for your BPF program. If not, the validator will deny your program. So this can be loaded into the kernel and it will run. But we need a program to load it in. You could use BPF tool to load in this program, but to do it from your own program is kind of nice, because then you can also control it using the communication channels that you create, which we have none of right now. I mentioned BPF tool can make a skeleton, and this is this header file. It's created by BPF tool, and I just include it. And it gives me access to, well, opening, simple open, and simple load, and simple attach. So simple is what I've just called my, well, I told BPF tool to prefix everything with simple, basically. I just gave it the name simple. So opening just opens up the SO file, or the object file. Then I load that into the kernel, and then I attach it to the hooks that is defined in the sections. And then I just loop forever and let the program do its thing, and then I destroy it afterwards. And as long when this user space program exits, the BPF program will automatically be detached. So if the user space program crashes, then the kernel will detach the corresponding BPF program for this hook. That's not the case for all hooks, and especially not network hooks they generally live forever, unless you explicitly detach them. So let's have a quick look here. And first off, I want to show you the BPF tool. What I can do with that is I can list out every currently running BPF hook. So these are the ones that's running on my system. And am I in simple? Nope. And then I can run my program, which I just call exec, and it's running. So if I run the BPF tool again, I see now a new trace point named handle clone. It has some more information there as well, but that's not as interesting. Now what you saw was that it's doing a BPF print K, but I'm not getting anything out. And the reason for that is that information is logged to a trace pipe in the kernel. So if I do this and I go and, is this the wrong? Yeah, it is. This is the one I was going to run. There we are. Now I have, and now you see there's stuff executing on the system. I have the PID, I have the parent PID. Let's stop it because it's going a bit fast. So I have the name of the application being run. I have the PID, I have the parent PID, and it's just logged to a pipe that I have access to. Of course, that part isn't as interesting, doing just logging to a pipe where you have to have access to actually look at it, but we'll get to how to do more interesting stuff. I also said we were making a skeleton, and the way we do that is by having BPF tool look at the object file. Exec bpf.o is the object file that I create from my C file, and I just call it, well, let's call it simple because that's what we did previously. And I failed making a pipe. There we are. So it creates a header file for you. It has a lot of information. It includes libbpf because this depends on libbpf. And you have some structs that you can access. It has a program, which is the program. It's the binary that the client compiles, basically, and a link to the BPF link. It also has these C++ handlers for me. So I can use C++ bindings, though the C++ bindings are just namespaced versions of the C bindings. They're not too interesting. So you do get some nice helper functions that you can use to create and manage your BPF objects. Okay. But currently we're not really doing much. Everything's happening in kernel space, and you kind of need a privileged user to even see what's happening, because you have to watch that trace pipe thingy. So let's see how we can communicate between the kernel space and the user space. And there's two ways of doing it, actually. I mentioned the eBPF maps, but you also have the .bss section where you can put simple things. And we'll start with the BSS section because it's the simplest, but you're probably not going to use it in many real-world scenarios, but it's nice to know about. So you make this int, which I call ppid, and I put it into the .bss section. Now the skeleton will then create a new entry in its skeleton structure, which is the BSS entries that I can use from userspace. So what I do is I read out the real parent process ID, and I check if the parent process ID is the same as the process ID I now am interested in. And then from user space, I just set the skeleton's BSS PPID to, well, whatever I get from the command line in this case. So basically this is watching one process and then printing out the information that you saw in the trace pipe if it's that parent process that's actually executing. So now I'm not interested in all the processes on the system, just this one. But this is also very limited, the BSS section, because it needs to be trivial types. But eBPF maps are way more. They have way more freedom. So you have multiple map types. We're not going to go through many of them. We're actually going to just look at two of them. We're not going to go into the details of what they are because they're very good for different applications, or the different ones are good for different applications. I'm not even sure if I'm using the most efficient ones in these examples, but they work. But I think it's tomorrow. There's a talk about SOCMap from the maintainer of the SOCMap functionality, and he's probably going to go more into details on how actually the SOCMap map works. But there are multiple map types, and we're going to start by using a ring buffer. So the way to do that, we'll start with the lower struct here, because that's actually defining the ring buffer. So you give it a type, which is the BPF map type ring buff. And then we say it has a number of max entries, which is 256 times 1024 in this case. And we put that struct in the .maps section, which gives us access to the map also in user space. So the max entries is basically the number of bytes you can have in the ring buffer. And it doesn't define what types it can hold. It can hold any type, basically. But what we'll use is this event struct that's over, which basically holds the exact same information as what we were printing out to the trace pipe. Now, to put this information into the ring buffer, you create an event struct. Basically how you would do it in NAC program. You have the PID, you have the PPID, and you have the command, and you just give that information to the event struct. And then you do BPF ring buff output to the events struct, and you give it the size of the object that you're putting on it. And then we can remove the BPF print K, because now we're basically sending this information up to well, technically someone else. So from the user space perspective, we need to attach to this map and make sure we can read events that's happening on it. So we get the file descriptor for this map. So while adding it like this, the BPF skeleton generation thingy will create an entry, which is maps.events. And you can use libEPF to get a file descriptor to that map. And then you can create a new ring buffer, and you can add a callback to it. Now this callback will then be called whenever something new is on the ring buffer. And then instead of just sleeping in the loop, I just consume the ring buffer whenever there's stuff in it. So the ring buffer consume will just make sure that whenever something new is on the ring buffer, I'll call the callback. And then you have to free the ring buffer when you're done with it. So in the consumer, in the callback, you get a context, you get some data, and you get a size. So the context is the user supplied context. You see I just sent 2 nulls here. So you can populate the context with actual user data. And then the data pointer is pointer to the data that's coming in on the ring buffer, and then the size is the size of whatever's on the ring buffer. So you can check that it's the expected amount of bytes. Just cast that over to an event struct, which I have access to, and then I just print it. And return 0, meaning I've handled this callback. So to use this in parent PID, I'm just checking what. So this is the PID of my current shell. So this is what I'll be watching. And that's 4352. So now I'm just watching the shell that's underneath, and I can do ls, for instance. No. This is running bash. What's going on here? Okay, this should have printed stuff out to the because it's the wrong one again. I thought I removed all this, all these. User space notification. Then I can do exec stuff, and it's now printed to std out instead of to this trace pipe. So now the user space is telling kernel space what to care for, and kernel space is sending data up to the user space so we can do sensible things with it. So currently I have almost a solution I needed to basically put stuff into a Cgroup. I could now follow a parent, and whenever that parent execs something I care about, I could put that into a Cgroup. But I'm more interested in when someone tries to run this particular binary. So the parent PID approach isn't really sufficient for my use case. So instead of just from the user space saying that watch this parent PID, I'm going to give it a list of strings basically, which is paths into the file system, and say that when these are executed, then you tell user space. And you do that with a map, just like we did to get data from kernel space to user space, because then we can send over more complex types like a string, and you can easily keep multiple entries. So like we did with the ring buffer, we create something in the maps section, but this time we make a map of hashes, or map type hash, where we have a maximum of 32 entries. This can of course be adjusted if you need more. I give it a key size and a value size. You can, and I'll show you later, you can say that this has a type of string, for instance, or a length of string, but this way it was easier when you're talking about strings, because they don't really have a type in C. So saying that we accept this amount of bytes basically was way easier. And then the value is just a unsigned 8-bit thingy, because I don't really gonna care about the value. I'm only gonna care about the size of the key, or the key. So instead of checking the parent PID with the PPID, I read in the command that's been exec, just like I did before. I just now push that further up in the stack, or in the function, and then I check, can I look up this element? Does this element exist in my map? If this exists in the map, then lookup element will return a handle to it, or an index to it. And if not, it will return 0. So if I can't find it, I'll just return 0, because then I'm not interested in this and I don't have to do anything more work in kernel. So that's basically the only change from the eBPF perspective, which is kind of nice. And on the user space side, instead of just writing to this PPID, I do the same as I did in kernel space when sending data back up. I copy the string I care about. I set a value. This is uninteresting, so I'm just setting it to 1. And then I update the exec names element. And when I've done that, the map contains some new data. So the next time the eBPF program is running, it will know what content is in there. And this is in this example just happening when we start up, but this could of course be dynamic. I could from user space both add and delete elements and do whatever I want. But also for this particular example, one thing to note here is when I update elements from the kernel space, the API is basically the same as for user space. But there is a way to distinguish it, and that is looking at BPF _ map _ update LM. The double underscore is the libbpf API, which is available to you in user space. If there's a single underscore after these functions, then you're in kernel space. So if you're not really sure if this is kernel space or user space code, just look at the functions that you're calling. They look very similar, but one of them has a double underscore somewhere. So after this, whenever my process is executing, I can put it into Cgroup. I'm not going to show how to do that, because that you can look at other talks. But what you need to do is you need to clean up after exit. If not, you have like just heaps of Cgroups lying around empty, and it's not really nice. It's not critical to do, but it's nice to clean up after yourself. So we need to add another BPF program that cares about system exit or process exit. And we need a map to communicate between the two eBPF programs. So if we want to make a map to monitor between, or to communicate between two eBPF programs, you just make a new map. And they don't have to, it's not a difference from if you want to communicate to user space. So in this case, I also make a map type hash. This time I say that the type of the key is a PID and the type of the value is a PID. And I keep 8K entries. So when I, in this case, have decided that this is interesting for user space, I put it into the monitored map. Basically, I put the PID that is being exec into the monitored map, and then I send the information up to user space. So now this monitored is just a map of processes that I'm currently monitoring. And now I need a new eBPF program, which then I hook into the sched process exit trace point instead of the exec, which I did previously. And this is kind of similar to the previous one. I do get my thread ID and PID. And then I check if, well, first off, I'm actually checking if it's the process or the thread that's exiting. If the thread is exiting, I don't want to do anything. But if it's the PID that's exiting, then I kind of want to do my work. And the only thing I do, I try to delete the element itself. If I successfully delete it, then I knew it was there, and this is a monitored process. So if I deleted it, I populate the event struct again. This time I add a type just to make it easier for userspace to distinguish between exec and exit. And I tell userspace that this happened, and now userspace can do its work. And of course, if it's not monitored, I just exit because I don't care about this process. So now I have all the building blocks to solve the use case that I wanted. So let's see what we want to monitor. Not there. I want to see what's the bash process. Nope. Make Cgroup. Pretty sure this is the correct one this time. So I run this thing, and I'm basically only monitoring that bash is executing. And if bash is executing, I'm giving it 200 megs. So this is just the format I made for the argument parser. So now I'm monitoring bash. So if I down here start bash, I can see, okay, what am I? I'm 14.057. Now, if you're familiar with Linux and Cgroups, there's this magical folder, sysfs Cgroup, and this now has a eBPF managed thing, which my userspace program creates. Just create a folder called eBPF managed. And in this, I have this folder 14.057, which is the Cgroup I created to monitor this bash process. So I can have a look at it. Sysfs Cgroup 14.057. And these are the processes that's currently in it. Now 14.057 is of course my current bash process. 14.127 is the cat process that I just created. So that one will always change. If I create another bash session, and I enter bash, then I see I have sysfs Cgroup eBPF managed. Oh, this was not easy to see. I now have two folders, which are two distinct Cgroups. If I exit one of them, that's cleaned up. And the creation and cleanup of the Cgroups themselves are done by the userspace program, not by the eBPF program. And also just to show that I have actually limited the memory. What's the memory.max? Oh, of course. I don't have permissions to do that. Oh, double dot. No wonder. So that should be 200 megs. Ish. Okay. Now, currently, we only used one type of hooks. We only did trace points. So currently we're only tracing programs on the system, which is fine, but there's a lot more you can do with eBPF. So you can connect programs to the Cgroup itself, like I said. You can connect it to a network interface. You can connect it to not sure if you can connect. Yeah, you can connect programs to devices on the system. So let's look into how you can connect a network program to the Cgroup itself. So I create a Cgroup, and now I want to actually do something more than just limit the memory. I also want to, say, do traffic shaping or some decision on the networking layer of processes that I put into this Cgroup. And for this, I created some very simple eBPF programs. So we connect to the Cgroup SKB egress and ingress hooks. So basically, whenever a packet is leaving or entering this Cgroup, or leaving or entering something in the Cgroup is more correct probably, I want to run these programs. And they are, as you can see, dead simple. They're not really doing much. If this flag is set, then I drop all the packets, and if not, I accept them. I don't care about the memory context I get in, the skey buff. I could, of course, monitor that or look at that and see that, okay, this only holds for UDP packets, or TCP only for TCP packets, or I can look into the data that's actually there, which is the full packet structure. In these hooks, I can't actually modify the contents of the packets. That's not allowed. They're read-only. In other hooks, I can. So kind of depends on what you want to do, which ones you want to use. But in this one, I don't really care. I'm just dropping packets or allowing packets. So from the user space, all I have to do is set this drop. And but I also need to attach it to the Cgroup itself. So I mentioned how to attach a BPF program depends on what type of BPF program or what type of hook you're attaching to. With the trace points, it was pretty easy. You just, with the skeleton, you just tell it to attach because it knows where to attach. But for Cgroups, you have to open a file descriptor to the Cgroup itself. So that's just the directory path of the Cgroup you're interested in. And then you say program attach Cgroup with the egress program and the ingress program to that file descriptor. So it's not that much harder as long as you use something relatively same like libbpf. Because that does all the work for you in the background, which is very nice. So that was a bit fast. So to show that, I do the same thing, but with the Cgroup network thing I made. And now I'm in a Cgroup. Let's just. So now this thing is in a Cgroup. And if I now want to curl writing is hard, especially hitting keys. So you see it works quite well until sometimes suddenly it hangs. So currently I allow packets for 10 seconds and then I block them for 4 or something like that. And now it works again for a good amount of time until every packet is suddenly dropped again. And that's the hangs you see. And you can do way more complex stuff than this with the networking subsystem. You can. I have a plan of using it to, for instance, push how to proxy stuff down to the kernel instead of having to do those decisions in user space. So everything from the machine is then proxied through a proxy, but then I have to actually inspect the data and see that, okay, this is actually a HTTP packet, so that's pushed to the proxy, and you can inspect a lot of data through eBPF as long as you use the right hooks. Because all of the, at least most of the networking hooks, you get this SK buff, which has all the data for the network packets. You have the raw bytes if you want to inspect them, but and this is for all hooks. That doesn't mean you can read them. So some of the fields in this SK buff might not be available for you depending on what hook you're using, and they might be read-only. You might be able to write to them. It all depends on what hook you're using. So if you have a use case that you want to solve, you need to figure out what's readable, what's writable, what's not even available, and then make a decision based on that for where in the networking stack you are actually attaching. So yeah, any questions? Yes?
What version of Linux kernel supports the extended?
It depends on what hooks you need to use, and also what library you want to, or what level of abstraction you want to use. Because it's, I think, as far back as 5.15, you at least have some support for it. But a lot of stuff is coming, like there, it's always developing. I'm not really sure, for instance, with the sock map stuff. I think you need to get to at least 6 something kernel to be able to use that. And there's probably new features being developed as we speak for it as well. So you have to look at what you need to use and figure out what kernel versions that's on. Any more questions?
So actually,
Yeah.
when you say that it's not available, does it mean that you, like, are you talking about the case where you have this same buffer structure but you can't read some of it?
Yes,
And
that's correct.
What stops you from reading? Is it the verifier that tells you no? Or?
Yeah, I'll repeat the question because there might be some people watching this later as well. So the question was, is it the case that in this SK buff, that some of the fields exist but are not readable, and how do I forgot the full train? How do you?
Are they not readable? Is it
Yeah.
compiler verifier or something else?
It's. I think it's not compiler verify. Yeah, it's verified by the compiler. When I try to, so it's verified by either verifier or the JIT compiler to check that you're only accessing data that is readable or writable for you. So they do verify it, and you will not be able to upload a program if it violates the whatever's readable and writable. I think that was the result, I think, when I tried it out, but I might be wrong. I don't think it's a runtime error. But yes, it's in theory the same struct, but then some things are marked as inaccessible. Yeah. Any more questions? No? Okay, then thank you.